Welcome. In this video, we're going to be looking at connecting the dots between what a definite integral means and how it will relate to the evaluation theorem. And we're beginning to understand the idea that a definite integral represents the area under a curve. So we've introduced this new notation. Again, we might not fully understand it yet, but the idea here is we're dealing with this integrand. And by that, I mean basically the function y equals theta. And if we wanted, we could call it y equals x. And what does y equals theta or y equals x look like? Well, if we were to graph it on a Cartesian plane, y equals theta or y equals x, we're using theta for our independent variable, is a diagonal line right at a 45-degree angle. And so then we have these bounds. We're going from pi to 2 pi. And so the idea here is we're trying to connect the dots with the fact that the integral represents the area under a positively oriented curve. And in this instance, we're ending up with the shape of a trapezoid. I'm going to take that trapezoid and draw it on its side so we can see that better. Now, the area of a trapezoid is a regularly known formula. Area is the average of the bases, so b sub 1 plus b sub 2 over 2 times the height. Essentially, it's the area of a rectangle, but we're averaging those two bases. So when we think about that top base, b sub 1, the height of that, if I were to plug in x equals pi or theta equals pi, I would get out y equals pi. So this length is pi, and then b sub 2, that bottom length, would be 2 pi. And then the height is the distance between pi and 2 pi, which is, of course, 1 pi unit. So in this instance, the area, because this is a regular geometric shape, is that top base pi plus the bottom base 2 pi, all divided by 2 times that height, which is pi units. So that is 3 pi over 2 times pi, or 3 pi squared over 2. That is the area of this curve. The area under the curve. That is what this definite integral represents. Erase. There we go. That's what the definite integral represents. It tells me that area. And we've already done an example where we sort of saw the evaluation theorem. So let's just look forward and connect that idea. So the idea here, if I was dealing with the integral from pi to 2 pi of theta integrated with respect to theta, we're going to use that power rule, which we already know, which gives us theta squared over 2, and then we evaluate from 2 pi to pi. So that is the same as 1/2 theta squared evaluated from 2 pi to pi. I pulled that constant multiple in front, and that is 1/2 2 pi quantity squared minus pi squared, which is 1/2 times 4 pi squared minus 1 pi squared, which again gives us that same answer, 3 pi squared divided by 2. So really all we're doing here is we're connecting the dots to the fact that the definite integral, when we evaluate it, represents the area under a curve. So looking at this next example here and moving forward to what we're going to be seeing a lot more of in section 5.4, in this instance, if I gave you this integral and I said, hey, evaluate it, you would say, well, that's my function, y equals s squared. And if I were to graph that, it would look like a parabola. It's opening up on both sides. It's symmetric. But because our bounds are from 0 to pi over 3, I'm sorry, not pi over 3, 0 to 0.3, we're ending up with this irregularly shaped area over here, okay? Now, is this a geometric shape that we know the formula for? It's not. I can't figure out what that shape would be, or the area of this curved triangular region without using the definite integral. Okay, so this is where we're going forward. This is what we're moving towards, using that next step. So if I were to evaluate, say, s squared and find that integral value using the power rule for integration, that would be s squared over 3 evaluated from 0.3 to 0, which is the same as 1/3. Excuse me, I made a typo there. I'm doing this really rough and quick here. That is actually s cubed over 3 by the power rule. So that is 1/3 times s cubed, and we're evaluating that from 0.3 to 0. So the 1/3 comes in front as a constant multiple, and 0.3 cubed, 0.3 quantity cubed minus 0 cubed, 0.3 cubed is 0.027 over 3, and then minus 0, that term of course goes away. So when I divide this by 3, the area under the curve is 0.009. And so that's the idea. That's what we need to connect together. All right. So moving forward, we're going to be using all of our integration rules, and we're going to be using them to define the idea that the integral of a curve, if the curve is over above the x-axis, a positively oriented curve, that will represent the area.